Okay. Expansion. Under binomial expansion, we look at, we need to define it. We need to know the meaning. We now do Pascal's triangle. Also, we'll revise factorial and combination. And now the binomial theory. From there, we'll get all this general term, middle term, and the application. So let's start with the first, the definition. Definition. Binomial, from the name bi, two. So any algebraic expression that has two terms is called a binomial. Yes, like saying that if you have like A plus B is a binomial, 2x minus 3, 5x plus 2, they are all binomial. Bi means two. The name bi means two. Y norm means them. So any algebraic expression that has two terms is called a binomial. So about Pascal's triangle. So you will notice that if from our basic algebra, that if you have A plus B raised to the power 0, the answer is 1. A plus B raised to the power 1 is A plus B. While A plus B raised to the power 2 is A squared plus 2AB plus B squared. Let's do 3. We now get something from this. You have A cubed plus 3 A squared B plus 3 AB squared, and finally B cubed. So you notice that we are forming, seems we are forming a triangle here with the coefficients of the terms. Like from the first one, 1. From the second one, the coefficient is 1. The second one is also 1, 1, both of them. So you notice that something like this, 1, 1, the second term. The first and the second, the coefficients are 1, 1 each. Also, the third term here, we have 1, you have 2, and we still have 1. So the fourth expansion will have like 1, 3, 3, 1. So we are forming a triangle. This triangle is called what is called Pascal. So this triangle formed here is called the Pascal's triangle. So from this you can still get the coefficient of the next term as 1, 4, 6, 4, 1. So you always, to form a triangle, that's what we call a Pascal's triangle. So factorial. So factorial is written as factorial. So whenever you see something n factorial, is always n multiplying the terms down to 1. And formally we take n must be greater than or equal to 0. Okay, let me just, from this we can still get a very important stuff here, because you can still write it as n times n minus 1 factorial, because n minus 1 factorial will multiply n minus 1 times n minus 2 down. So that's another, or we can still stop as n minus 2 factorial. From there we see that 1 factorial is 1, and also 0 factorial is also 1, because from what we've just written, you'll be wondering how come 0 factorial is 1. You see that from n factorial equals n times n minus 1 factorial. you see that if n is 1, that is 1 factorial equals 1 minus 1 factorial. So 1 factorial we know is 1. 1 factorial is 1 and 1 minus 1 is 0. So 1 times 0 factorial. So that's it. So the next thing is to revise combination. But we are doing it because combination has something to do with factorial. So it's written combination. So n combination R is written as n combination R, or some will write it this way. See if it's a matrix. So anyone or, so that means n combination where n must be greater than 0 and R is greater or equal to 0. So that's it. And how do you expand this? N combination R is written as n factorial over n minus R factorial R factorial. Yes. So that's it. That's what you have to know. So example, if you are given 5, you are given 5 combination 2, we have 5 factorial 5 minus 2 factorial 2 factorial, which is 5 factorial over 3 factorial 2 factorial. We can still go further as 5 times 4 times 3 factorial over 3 factorial times 2 factorial. So we have 5 times 4, and 2 factorial means 2 times 1, which is 10. The answer is 10. So that's how we expand. That's how we write combination. So let's now enter the main thing, which is our proper binomial theorem. Very, very important. You notice that using Pascal's triangle takes time as well. Yeah, it's not efficient if n becomes large. So I'm saying that if n becomes like from 100, 10, 20, so we now apply what we call binomial theorem, which states that if you are given to expand any binomial of this form, we can bring in combination as is written as n combination 0a n b0 plus n combination 1 a n minus 1 b1 plus n combination 2 n minus 2 b2 down to n combination n 0 bn. So you notice that we started from 0, n combination 0 an. That's a starts from the highest number and decrease down to 0, while b starts from the lowest, which is 0, and increase to n. So this is very, very, very important. So it helps us to expand better and faster. So example, if you are given, okay, let's use s plus maybe x plus 2 raised to power 2. Our n is 2, so 2 combination 0 x2 2 0 plus, or maybe, okay, let me use 3 here so that we differentiate it from. So 2 combination 1 x1 3 raised to power what? 1. Do you know? Plus, we stop here because we end in n. The last number n, 2, 2. So we end here, which is 0, 3, 2. So our answer is 2 combination 0 is 1. So we have x squared times 1. That's 1 times x squared times 1 plus this combination, that is 2. So 2x times 3, which is 6x. And finally, this is 1, 1. So 3 squared is 9. So that's it. So it helps us to solve it helps us to expand binomial better and faster, and also solve a harder question than using Pascal's triangle. So we now notice something from this, very, very important. You will notice that the number of terms, there are some things we need to observe here. The first thing we'll observe, one, that the number of terms is always n plus 1. That's for any binomial expansion, that the number of terms is n plus 1. Yes, if you check these two, how many terms? 1, 2, 3. If it's 1, we have 2 terms. If it's 0, we have 1 term. So that's the first thing we observe. 2, that the coefficient of the binomial coefficient increases from 0. That's the coefficient, that's the combination 0, 1, 2 to n. So that's another thing you observe. And n and a decreases from n to 0, while b increases from 0 to n. These are very, very important. And the final observation here that is very important is the particular term. We can get a general term from this. You notice that if, okay, let's go to the general term of a binomial expansion. The general term, I'm saying that if you have a plus b, and we've noticed is this n minus 2b till you get to n combination n's. We now observe some. This is the first term. This is the second term. That's our third term. So let's leave others. We can get something from this. First term. So if you are looking for the first term, you notice that the r, whatever that is here, is 1 down from the term. See, first term, this is 0. Second term, this is 1. That's what you notice. Again, the power here has something to do with this. You notice that n is the same thing as n minus 0. Yes, this is 0. This is like n minus 0 is also n. Here, 1, this is n minus 1. 2, n minus 2. So why the final thing here, whatever that is here is here. 0, 0, 1, 1. So with that, we can see that if you are looking for any particular term, for example, if you are looking for r plus 1's term, the formula is n combination r. Remember, I told you since this is first term, we have 0. So we can write first term as 1 is 0 plus 1. Do you get? That's how this r becomes 0. So that's now our formula. A n minus r b r. This is very, very, very important. Very, very important. This is now the particular. If you are looking for any particular term, no need of expanding. We just pick our r from the, depending on the example. I'm saying that if you are asked to find, maybe if you are asked to find the fourth term. Fourth term of x plus 2 raised to the power 6. So you don't need to waste time to get all the term and from there pick the fourth term. No. So you see that fourth term means 3 plus 1. So our r is 3. So we don't need to, our n is 6. So 6 combination what? 3. Our a is x. So x raised to the power what? Remember, 6 minus 3. And finally 2 raised to the power 3. So that's our fourth term.